So, geometry for CAD, like we've discussed before, is a very, very important topic, as important as algebra. And in geometry, we have two main chapters: lines, angles, triangles, and mensuration. In the first one, they can ask you what the angle is or what the length of the line is. And in mensuration, we will be asked either the area or the volume. 70% of the questions are from area and volume. So let us start with the first chapter, lines, angles, and triangles. So let us run through the basics. Lines can be parallel, intersecting, or transversal. The proportionality theorem is used many a times in CAD exam. So if we have these three are parallel lines and these two are transversals, then their ratio will be proportional. They will be proportional in length. AB upon BC will be equal to DE upon AF. About angles, we should know what the vertex is, and basically when two rays have the same starting point, they form an angle, and the common end point is the vertex. Now this again becomes very important, the relation between angles. So M1, M2 are parallel lines, and there's a transversal cutting through the two lines. Then angle A is equal to angle E, C is equal to G, B is equal to F, D is equal to H. These are corresponding angles. When A is equal to D, E is equal to H, C is equal to B, G is equal to F, because these are vertically opposite angles. And when the opposite interior angles are supplementary, so E plus C will be 180 degrees, D plus F will be 180 degrees. And finally, alternate angles. This is very important. With alternate angles, C is equal to F or D is equal to E, these will form a Z-shaped figure. They will form a Z, like the part that is shown in black. Alright. Now there are some terms that we should be familiar with. Acute angle from 0 to 90, right angle is 90 degrees, obtuse is from 90 to 180, reflex is from 180 to 360. Complementary when sum of two or more angles is 90 degrees, supplementary when sum of two or more angles is 180 degrees. We should know what a perpendicular bisector, angle bisector is, and what concurrent lines are, which intersect at the same point. Then types of triangles can be equilateral, isosceles, or scalene. Now let us see some properties of triangles. Sum of all the three angles will be supplementary. The three angles are supplementary. The exterior angle is equal to sum of the opposite interior angles. Angle opposite to the greater side is greater, and the side which is opposite to the greatest angle is the greatest side. Sum of any two sides will always be greater than the third side. This property has been used many times in the CAD paper. Let us take up a question. What will be the range of perimeter of a triangle with two sides 4 and 7? Now, question similar to this, the same concept was used, came in CAD a few years ago. So we know sum of any two sides is greater than the third side, so either 4 plus 7 will be greater than x, which will be the largest side, or x plus 4 will be greater than 7, where 7 is the largest side. So x should be between 3 and 11. So perimeter is in 3 we add 7 and 4, the other two sides, and in 11 we add 7 and 4, the other two sides. So this is the range that we get. Let's move on. This formula is very, very, very important. A upon sine A equal to B upon sine B equal to C upon sine C, where ABC are the sides opposite to angles ABC. In congruency of triangles, we can either use SSS, SAS, or AAS, and in similarity, all we need is either AA or SSS. Now, again, another very important formula used many a times in CAT, the basic proportionality theorem. AB upon BD is equal to AC upon CE. These two lines are parallel, by the way. And AB upon AD is equal to AC upon AE, AD upon BD equal to AE upon CE. Basically, we just take proportional sides, they will be equal. Okay. The ratio of the areas of two similar triangles is equal to the ratio of the squares of the corresponding sides. Okay, so area of triangles ABC, ratio of areas of triangles ABC and PQR, which are similar triangles, will be equal to AB square upon PQ square equal to BC square upon QR square equal to AC square upon PR square. And another specific case of use of similarity is involving a right angle triangle. Like these two triangles that are shown in the figure, these are similar triangles. Then here, AD squared is equal to BD into DC, or AB squared is equal to BD into BC, and AC squared is equal to CD into BC. This has not been in use that much, but we should be aware of this property of triangles. Now, Pythagoras theorem, we know in a right angle triangle, the square of the hypotenuse is equal to the sum of the squares of the perpendicular sides. Pythagorean triplets can be derived if one of the side n is an integer, and when it is odd, then the other two sides are n square plus minus 1 by 2, and when n is even, the other two sides are n square by 4 plus minus 1. So we should remember the first three triplets: 3, 4, 5, 5, 12, 13, and 6, 8, 10. And any of their multiples, for example, for 3, 4, 5, we get 6, 8, 10. That would also be a Pythagorean triplet. Now, there's a very important observation, and on the basis of this, we have another CAT previous year question. So, in a triangle, C squared is equal to A squared plus B squared, we know it's a right angle triangle. If C squared is less than A squared plus B squared, then right, we know that the side opposite to the smaller angle is smaller. Then if and vice versa, angle opposite to the smaller side is smaller. So C square, which has become smaller now, the angle will also become smaller, and it will be an acute angle triangle. If C square is larger than A square plus B square, then it's an obtuse angle triangle. Question which came in CAT used this property, that if it is an obtuse angle triangle, then C square should be greater than A square plus B square. This is what was used. Now let us move on to lines and points in a triangle. So the median joins the vertex to the midpoint of the opposite side, and it may or may not be perpendicular, may or may not be the angle bisector, right? The angle bisector will bisect an internal angle of a triangle. It need not pass through the midpoint of the opposite side, need not be perpendicular to it. Perpendicular bisector is the perpendicular line passing through the midpoint of a side. It need not pass through the vertex. This is very important, right? So this line L2 is the perpendicular bisector, where D is the middle point. This figure is not to scale. Please draw a 2-scale figure on your own so you understand better. Do not be confused by this figure. I'm so sorry. Now, what is the altitude? It's a line dropped from the vertex and perpendicular to the opposite side. It does pass through the vertex but need not pass through the midpoint of the opposite side. The perpendicular bisector passes through the midpoint of the opposite side. Now, in any triangle, the 3 medians are concurrent. So are the 3 angle bisectors, the 3 perpendicular bisectors, and the 3 altitudes. All of these are concurrent. Now let us see the important points of a triangle. Where these 4 altitudes meet is known as the orthocenter. Where the 4 medians meet is called the centroid. Where the angle bisectors concur is called the incenter, and where the perpendicular bisectors concur is called the circumcenter. And in an equilateral triangle, all these lines and points are the same. Okay. Now let us move on to some properties of this. Might seem a little scary, but to be honest, this has not been seen in CAT much. Okay, so it's not very important. I would go as far as to say that you can skip it, okay? But if you do have time, then this can be useful in 1 or 2 questions. Okay, so let's go ahead. The orthocenter where the altitudes meet, right? Now, in all of these figures, we'll try to find the relation between this angle BHC and the angle A. So here BHC plus A is 180 degrees. For in an incenter where the angle bisectors meet, this BIC is 90 plus A by 2, or it is 180 plus A by 2, right? And in a circumcenter where the perpendicular bisectors meet, angle BOC, the middle angle, is equal to twice of angle A. Now what else is there? Medians, they divide the triangle into 2 triangles of equal areas. What else is there? That medians, the centroid will divide the median in the ratio 2:1, where the side closer to the vertex is the larger one. Now we come on to the incenter, which is the meeting point of the angle bisectors. We can make a circle inside the triangle, hence the in circle, and the in radius will be perpendicular to the sides of the triangle, right? It may not correspond with the angle bisectors, but if you join the incenter to the sides of the triangle, then you get perpendiculars from the center to the triangle. Right, these are tangents. We can make tangents, the sides of the triangle are tangents to these perpendiculars dropped. Also, AB upon AC is equal to BD upon DC. AB upon AC is equal to BD upon DC. We've already seen this, right? It's the same formula every time. For circumcenter, If it's an acute angle triangle, the circumcenter will lie inside. We can visualize this, right? Try to visualize this, that if it's an acute angle triangle, circumcenter lies inside the triangle, like we can see in the figure. If it is obtuse angle triangle, the circumcenter will lie outside the triangle, and for a right angle triangle, it lies right on the middle of the hypotenuse. So this third point is very important. In a right angle triangle, the circumcenter lies on the middle of the hypotenuse. These are some remaining important formulae. The first one, the angle bisector theorem, is very important. Do not skip this. So if this line AD is the angle bisector of angle A, then BD upon DC is equal to AB upon AC, like we seen just now. Area of a triangle is given by Heron's formula. We know it's half base height. Apart from that, it's given by Heron's formula, S minus A, S minus B, S minus C under root, where S is the semi-perimeter. There are other ways to find the area. You can see these formulae. These are not very important, not used a lot in GAT. Now again, a very important formula, cos theta is equal to A square plus B square minus C square upon 2AB. Many questions are solved using this formula. So I'll mark this as very important. Alright. So this was the theory for lines, angles and triangles. Now we can move on to mensuration, and we'll have covered most of the power geometry. Bye bye.